In fluid dynamics, the drag coefficient is a dimensionless quantity that is used to quantify the drag or resistance of an object in a fluid environment, such as air or water. It is used in the drag equation, where a lower drag coefficient indicates the object will have less aerodynamic or hydrodynamic drag. The drag coefficient is always associated with a particular surface area. The drag coefficient of any object comprises the effects of the two basic contributors to fluid dynamic drag, skin friction and form drag. The drag coefficient of a lifting airfoil or hydrofoil also includes the effects of lift-induced drag. The drag coefficient of a complete structure such as an aircraft also includes the effects of interference drag. Definition: the drag coefficient is defined as where is the drag force, which is by definition the force component in the direction of the flow velocity, is the mass density of the fluid, is the speed of the object relative to the fluid and, is the reference area. The reference area depends on what type of drag coefficient is being measured. For automobiles and many other objects, the reference area is the projected frontal area of the vehicle. This may not necessarily be the cross-sectional area of the vehicle, depending on where the cross-section is taken. For example, for a sphere. For airfoils, the reference area is the planform area. Since this tends to be a rather large area compared to the projected frontal area, the resulting drag coefficients tend to be low, much lower than for a car with the same drag and frontal area, and at the same speed. Airships and some bodies of revolution use the volumetric drag coefficient, in which the reference area is the square of the cube root of the airship volume. Submerged streamlined bodies use the wetted surface area. Two objects having the same reference area moving at the same speed through a fluid will experience a drag force proportional to their respective drag coefficients. Coefficients for unstreamlined objects can be 1 or more, for streamlined objects much less. Background: the drag equation is essentially a statement that the drag force on any object is proportional to the density of the fluid and proportional to the square of the relative speed between the object and the fluid. CD is not a constant but varies as a function of speed, flow direction, object position, object size, fluid density and fluid viscosity. Speed, kinematic viscosity and a characteristic length scale of the object are incorporated into a dimensionless quantity called the Reynolds number or is thus a function of. In compressible flow, the speed of sound is relevant and is also a function of Mach number. For a certain body shape, the drag coefficient only depends on the Reynolds number, Mach number and the direction of the flow. For low Mach number, the drag coefficient is independent of Mach number. Also, the variation with Reynolds number within a practical range of interest is usually small, while for cars at highway speed and aircraft at cruising speed the incoming flow direction is also more or less the same. So the drag coefficient can often be treated as a constant. For a streamlined body to achieve a low drag coefficient, the boundary layer around the body must remain attached to the surface of the body for as long as possible, causing the wake to be narrow. A high-form drag results in a broad wake. The boundary layer will transition from laminar to turbulent providing the Reynolds number of the flow around the body is high enough. Larger velocities, larger objects, and lower viscosities contribute to larger Reynolds numbers. For other objects, such as small particles, one can no longer consider that the drag coefficient is constant, but certainly is a function of Reynolds number. At a low Reynolds number, the flow around the object does not transition to turbulent but remains laminar, even up to the point at which it separates from the surface of the object. At very low Reynolds numbers, without flow separation, the drag force is proportional to instead of. For a sphere this is known as Stokes Law. Reynolds number will be low for small objects, low velocities, and high viscosity fluids. An equal to 1 would be obtained in a case where all of the fluid approaching the object is brought to rest, building up stagnation pressure over the whole front surface. The top figure shows a flat plate with a fluid coming from the right and stopping at the plate. The graph to the left of it shows equal pressure across the surface. In a real flat plate, the fluid must turn around the sides, and full stagnation pressure is found only at the center, dropping off toward the edges as in the lower figure and graph. Only considering the front side, the of a real flat plate would be less than 1. Except that there will be suction on the back side, a negative pressure. The overall of a real square flat plate perpendicular to the flow is often given as 1.17. Flow patterns and therefore for some shapes can change with the Reynolds number and the roughness of the surfaces. Drag coefficient CD examples. General, in general, is not an absolute constant for a given body shape. It varies with the speed of airflow. A smooth sphere, for example, has a that varies from high values for laminar flow to 0.47 for turbulent flow. Aircraft, as noted above, aircraft use their wing area as the reference area when computing, while automobiles use frontal cross-sectional area. Thus, coefficients are not directly comparable between these classes of vehicles. In the aerospace industry, the drag coefficient is sometimes expressed in drag counts where one drag count equals 0.0001 of a. Bluff and streamlined body flows. Concept, drag, in the context of fluid dynamics, refers to forces that act on a solid object in the direction of the relative fluid flow velocity. The aerodynamic forces on a body come primarily from differences in pressure and viscous shearing stresses. Thereby, the drag force on a body could be divided into two components, namely frictional drag and pressure drag. The net drag force would be decomposed as follows. Where is the pressure drag coefficient, is the friction drag coefficient, equals tangential direction to the surface with area dA, equals normal direction to the surface with area dA, is the shear stress acting on the surface dA, is the pressure far away from the surface dA, is pressure at surface dA, is the unit vector in direction normal to the surface dA, forming a unit vector. Therefore, when the drag is dominated by a frictional component, the body is called a streamlined body. Whereas in the case of dominant pressure drag, the body is called a bluff body. Thus, the shape of the body and the angle of attack determine the type of drag. For example, an airfoil is considered as a body with a small angle of attack by the fluid flowing across it. This means that it has attached boundary layers, which produce much less pressure drag. The wake produced is very small and drag is dominated by the friction component. Therefore, such a body is described as streamlined, whereas for bodies with fluid flow at high angles of attack, boundary layer separation takes place. This mainly occurs due to adverse pressure gradients at the top and rear parts of an airfoil. Due to this, wake formation takes place, which consequently leads to eddy formation and pressure loss due to pressure drag. In such situations, the airfoil is stalled and has higher pressure drag than friction drag. In this case, the body is described as a bluff body. A streamlined body looks like a fish or an airfoil with small angle of attack, whereas a bluff body looks like a brick, a cylinder or an airfoil with high angle of attack. For a given frontal area and velocity, a streamlined body will have lower resistance than a bluff body. Cylinders and spheres are taken as bluff bodies because the drag is dominated by the pressure component in the wake region at high Reynolds number. To reduce this drag, either the flow separation could be reduced or the surface area in contact with the fluid could be reduced. This reduction is necessary in devices like cars, bicycle, etc. to avoid vibration and noise production. Practical example, aerodynamic design of cars has evolved from 1920s to the end of 20th century. This change in design from a bluff body to a more streamlined body reduced the drag coefficient from about 0.95 to 0.30. Time history of aerodynamic drag of cars in comparison with change in geometry of streamlined bodies. See also, automotive aerodynamics, automobile drag coefficient, ballistic coefficient, drag crisis, zero lift drag coefficient, notes. References, Clancy, L.J. Aerodynamics. Pittman Publishing Limited, London, ISBN 0-273-01120-0, Abbott, Ira H., and von den Hoff, Albert E. Theory of Wing Sections. Dover Publications Incorporated, New York, Standard Book No. 486-60586-8, Herner, S. F. Fluid Dynamic Drag. Herner Fluid Dynamics, Bricktown, NJ, USA, Bluff Body, http www.engineering Wirewedge Lecture /Bluff %20 Body 2 PDF, Drag of Blunt Bodies and Streamlined Bodies, http www.princeton.edu Bicycle Web Blunt HTML, Hucho, W.H., Jansen, L.J., Emmelman, H.J. 6, 1975, The Optimization of Body Details, a Method for Reducing the Aerodynamics Drag. SAE 760185.